Can you say yes? Yes, I could see. Thumbs up. That's so cool. Guys, thank you for coming. Welcome to the New Generation Space Architecture. This is Anastasia, the CEO of Stellar Amenities, your host for today. And thank you everyone for coming again. And here's Daniel. He is lead designer at SOM. He is going to be our speaker. And today marks our third event. We are proud to be able to host it. One second. Host it today with you. Before we get started, I'd like to express my sincere appreciation to those who generously helped us to make this event come together to become a success. Thank you, Daniel, for accepting our invitation to come and speak at Space Architecture Talks. And thank you, Stellar Amenities event producer Jessica Agostina and our communication intern Eden Winger for putting everything together. And let me just kind of pull over some slides on what space architecture is. One second. I hope you can see my screen. So Space Architecture Talks is the first and only space architecture-related events that we are occurring pretty much every month. We had a break this summer, but we're going to continue our event hosting. And these events, we are featuring space architects and futurists. And hosted by Stellar Amenities, Space Architecture Talks is designed to bring awareness about space architecture to the broader space community and to address the challenges of becoming multiplanetary species and how these challenges could be mitigated by human-centered design. And on the first talk, we were really excited to see 200 plus attendees from 29 countries joining us, and space architects from NASA and CRH and Cushing Terrell. We were talking about what are resemblance of space architecture, what's the resemblance between space architecture and what we see in sci-fi movies. And then on the second event, we had a philosophical discussion of faith and culture and society. And that time we featured Ariel Egblow. She is director of MIT Media Lab Space Exploration Initiative. And also we had Frank White, who is the space philosopher, as well as he's the author of the Overview Effect Space Exploration book. And then who I am and what we do. So Stellar Amenities, I'm the CEO of Stellar Amenities, as I said before, and we are the first and only company to complement space-epic habitats with lightweight and reconfigurable elements to improve well-being in space. And in order to see the previous series of our space architecture talks, you can go to YouTube channel Stellar Amenities and find the previous talks. This time I'm gonna end the presentation. One second. And here we go. So today we are here to talk about what are design principles towards achieving our sustainable future on the moon, and to discuss how the international alliance between private and public space and non-space entities are investigating strategies for off-world architecture. On this note, let me welcome Daniel, a lead architecture designer at SOM in New York City. His passion for space and cross-sector research has led to initiate and foster public and private partnerships with government and academia for future exploration initiatives. By working with partners at ESA and MIT, his work has expanded to the role of the architecture, engineering, and construction industry through international cross-sectoral collaboration. His work in interdisciplinary research and space architecture has been exhibited, presented, and published at the 70th International Astronautical Congress, AIAA AIAA Year in Review, Architect Magazine, American Society of Civil Engineers, New Scientist Life, National Space Society, and more. Prior to SOM, Daniel worked for Frank Gehry Partners, Gehry Technologies, NASA, and HKS Line. The event is kicking off from the presentation of Daniel, where he's gonna walk you through on the Moon Village proposal that he worked with SOM, MIT, and ESA. And then after presentation, we're gonna jump into discussion about what are the principles of creating a new generation of space architecture. If you have any questions, please um, um, type them into the question tab. You see it on the right. And we're going to answer to as many questions as we can at the end of the presentation, at the end of the session. And Daniel, thank you again, and welcome. I'm really welcoming you to the virtual stage. Please kick off the presentation.
Hey, Anastasia, thank you for that. That was nice. So welcome to everybody listening. I'm going to go ahead and share my screen. Let me know if you can see it. Just give me a second here. Whoops. All right. Can you guys see this?
Yeah.
Yeah, perfect. So I'll start from the top. As you know, this project that we're going to talk about a little bit today is coming from my work at SOM. I've been with SOM for a little bit more than 3 years now, and I have a background in architecture, of course, trained as an architect, and I've also had the privilege of working for NASA in the past, which somewhat ties into this effort. One of the key things I wanted to kind of get off today is that the work at SOM in the world of architecture for terrestrial applications is very much, about responding to the environment. The environment around the world changes, and societies also have, different expectations of what architecture can be, and that's influenced by technology and different, methods of using technology. And so at SOM, we work on projects across scales, everything from, small experimental projects which make use of new technologies to trying to confront the challenges of building a large piece of infrastructure, which are skyscrapers in very dense environments. And so a lot of the processes and methods that we develop to confront these challenges are really kind of embedded in the practice of, how do we take high level integration and bring that into the nuance technological developments that are happening around the world with construction, manufacturing, and design. And so here are like 3 projects that are very interesting from an integration perspective that I've had the chance, or 2 of them I've had the chance to work on. And then when you kind of expand on what this means from a more philosophical perspective, we're in an age where technology is inspiration. A lot of the architectural concepts that you see evolving in the discipline are sometimes, somewhat haphazardly developed, where now technology is allowing us to think numerically through processes of building physics and how the building responds to the environment and how it has to work with new systems that are being developed to help improve society as a whole. And so technology is inspiration, but it also has to integrate a lot of different expectations. And on the left, you see a list of the different kinds of drivers that architecture has to confront, like environmental performance, energy, sustainability, new kinds of materials, efficiencies in structures, new kinds of structures, mechanical systems. Of course, comfort being kind of like the central aspect of designing, for a constrained environment, but also trying to tie that to a next generation of design processes, which has to do with computation. And we use computation to the advantage of being able to come up with better solutions. If you try to come up with a lot of options manually, you reach a limit before you come up with the best concepts. And so using computation to be able to integrate all of these different drivers allows us to produce solutions that otherwise wouldn't be generated. And so then the question is, first, we have to understand how architecture comes into being. And architecture, of course, requires raw materials, requires information coming from designers and scientists and engineers, and also it requires energy. And this also bleeds into the life cycle of an architecture, whether it's on Earth or in space. And when you think about architecture in space has to go a little bit above and beyond architecture on Earth, in the sense that it has to kind of disassociate itself from the environment, because it has to be shielded from that hazard environment. And so it has to reproduce and simulate all of the different processes that of a sustained ecosystem from the inside out. And that's kind of a key driver for how we think about architecture in the future, especially when you think about going to the space or beyond. And so this research project with ESA was initiated in 2017. And one of the kind of philosophical differences in thinking about international partnerships towards that work together to achieve these kinds of challenges is that here, we're thinking about an open architecture that invites expertise from multiple disciplines, from different industries, and that tries to, bring all of these different energies to produce an idea that wouldn't otherwise be possible if you only allow one industry or one entity to kind of work on these problems. And so this was a very, open exchange of ideas and open exchange of information, and trying to solve large scale problems, but also the small scale, which is what we're going to talk about today, which is that habitat architecture, which needs to happen if we're going to have a sustained, lunar presence or presence in space, since the human component becomes the most essential part of any exploration initiative in the future. And so now we're thinking about a completely different environment. On the moon, we have a completely different set of physics that we have to deal with. We have a lot of different hazards that we have to confront. And at the same time, there's a lot of unique opportunities which come in the form of industrial and resource exploitation processes that we can leverage. And so an architecture which is specific to this environment can come in the form of, well, there's different ways to approach it, but in this case, it comes in the form of a singular habitat that is a surface deployable habitat, and that needs to take place in the most optimal zone on the moon. And so the vision we developed for that was this space architecture, which becomes kind of like the nascent component of a much larger infrastructure, which then allows for multiple missions to take place over time, and which can expand on different technologies for testing and proving new capabilities. To start off, we took a look at two different paradigms. So this is something that I think has been done quite a bit, but people always refer to the historical models, which are the rigid structures, and then we look at the more recent expandable shell technologies. And the idea here was to try and bring a hybrid approach to this problem of habitat on the surface application. And so we developed a unique methodology just to get this, developed over time. And first, we have to look at mission requirements. The habitat has to accommodate a certain number of crew, and so we define that from the very beginning. Then you also have to define the duration of the mission that your habitat architecture is going to be enabling. And at the same time, you want to make sure that there's a specific site or an area of interest that you want to aim for. There's different conditions around the moon, and so you want to make sure that the architecture is already starting to take those specificities into consideration as you're developing the architecture. Of course, you have to come up with a concept of operations. The concept of operations can take you down the line of everything from transportation all the way to how you get it to the surface and deploy it. And then there's system level drivers. So you have to consider systems like energy, thermal structures, crew accommodations. A lot of these systems all play a role in how you develop this architecture. And assumptions, you have to make assumptions because not everything is available. There isn't every kind of capability that you would need to be able to develop a habitat architecture fully. So you need to make assumptions on what will be available, 5, 10, 20 years from now. And all of this helps inform the architecture as it develops. In terms of mission phases, as you develop a habitat architecture, you have to consider testing. So if you come up with in this case, we came up with an exterior shell structure, which is completely unique in its configuration. And so there has to be testing between interfaces. There has to be testing in the way that you pack it, in the way that you secure it. And you also have to consider testing in terms of launch vibrations and transfer loads. And so that's the case for any kind of payload or architecture of this scale. And because you're also pressurizing the system, you would have to do some extensive leak testing. And all of this ties into how you design those different interfaces. In terms of launch, you're limited by the mass and the volume dimensionally. And so if you look at the different launchers that exist today, a habitat like this would not be actually quite feasible. So you have to anticipate either, customizing the different launcher capabilities, or hoping that companies like SpaceX can bring a new kind of technology that would allow us to send much bigger payloads to the surface of the moon or beyond. You also have to consider how you dock to this architecture. So whether it's integrated into the habitat, or if there's like an additional component, you want to make sure that that's also part of your design process. Landing is a very, very extreme constraint, because a payload of this size will require its own landing piece of infrastructure, and landers for a habitat of this scale don't exist and are not anticipated to exist anytime soon. But maybe with different companies working on landing smaller payloads, we'll get to that capability. And so you have to consider how you land the mass, where you're going to land it, the kind of different interactions that are going to happen between the lunar surface and the lander. And all of this also feeds into how you get it to its final destination, how you assemble it, and how you deploy it before putting it into operations. And so this was the kind of beginning of the concept development. You can see here that we have a hybrid structure. The hybrid structure depends highly on being able to resolve these interfaces, but that also is tied together with the geometry of the architecture. And the geometry has a lot to do with how you distribute the loads from the inside. So from a pressurization perspective, you want to analyze how the loads are being distributed, but also where the weak points are. And in this case, the weak points are happening at the interface between the shell and the rigid frame, but also at the windows, which are inside of the frame. All of the mission components that we needed to be able to achieve this architecture include a habitat service module, and this would supply power to the habitat for thermal control requirements. So when you're actually in space and you're getting it to lunar orbit, you need to be able to condition the inside of the habitat to be able to maintain some of the critical infrastructure, like life control systems. And so you want to consider that you want to have a power capability that can give you enough energy to be able to power the thermal for that. Otherwise, you compromise your environmental control and life support systems, and then you don't have a working habitat when you get there. Our airlock modules, you also want to either make that, like I said before, part of the architecture in the habitat, or you want to design this separately depending on how you approach it. In our case, we designed this as a separate component to be able to increase the utilization of the habitat from a human-centered design perspective, because we didn't want to compromise the volume in the area that was associated with the direct activities inside of the habitat. And then you need a tug. So the tug is also a big piece of infrastructure to get it from Earth orbit to lunar orbit. And this would most likely be, pretty large. It would be something that you could either transfer on a separate launch or as part of the habitat if the habitat was small enough and you had the right launcher. And the lander would also be a large piece of infrastructure. So the purpose of a lander would be to get it down to the surface, but you could also imagine using a reusable lander that could be either refueled on the surface once ISRU comes online, or you could bring additional fuel with you. But the lander has to be a reusable piece of infrastructure in order to be more sustainable. Just like the habitat, you can imagine the habitat having multiple life cycles as it evolves and different missions come online. Power station, this is something that is also very critical. In order to achieve independent solar power capability, you would need to deliver a lot of mass for solar PVs and the structures. And so a power station that is in the form of a nuclear fission generator would be most likely the most optimal solution. But because it's a hazard to the habitat, you don't want to have this inside of the habitat. You want to have it somewhere offsite. So it would either be delivered together with the habitat or on a separate launch, and then you would place it off the site, which means that once it's plugged to the habitat, it can power it continuously. But in the meantime, you need to have a small amount of power capability in the habitat to be able to maintain those thermal requirements for the life support system. And external radiators, you want to get all of the heat out of the habitat. Humans produce a lot of heat, and so that will require a lot of area that you have to consider. And it can also be part of the design of the habitat, or it can be something that's an additional component that interfaces with the habitat. I won't talk about transfer too much, but there are various kind of staging points that you can consider. The point here is that there's a certain amount of fuel that you have to consider for transportation, and all of that will feed into the kind of the mass budget as you consider different types of architecture. And then to get a little bit more into, I think what's important here is thinking about the crew and the different kinds of accommodations. So of course, crew accommodations will include private quarters, dining, communal spaces, workspaces, exercise areas, EVA, suit, donning and doffing, medical care, hygiene, translation corridors. And if you look at historical models, there's a wide range of numbers in terms of habitable volume. But in our study, we looked at all of these models, but we also wanted to optimize for long duration missions. And so we ended up coming up with a number that was about 80 cubic meters per person for this long-term duration, which was between 300 and 500 days. And that, of course, will put a lot of pressure on all the systems. But if we're going to have a meaningful presence, on the moon and be able to do some science, some serious science and serious industrial work, then you're going to need to provide that kind of volume for high performing, spaces. And of course, you also want to be conscious of budget requirements. So along with this volume comes the different kinds of equipment and systems that you will need, like the galley and food systems, waste collection and hygiene, sleep accommodations, health and clothing, operational supplies and maintenance. And each one of these will have its own, volume, power, and mass factors. And so you want to find a way to, put these all into a parametric model that can help you in designing this habitat architecture. Again, in terms of architectural considerations, there's a wide range of considerations that you have to consider. I won't go through all of these, but you kind of get a sense for, just how many intricacies and interdependencies there are associated with designing a habitat architecture. And I think one of the most important ones is the way that you integrate the different kinds of interfaces like lighting and windows. This has to be something that is, of course, easy to use, but you also want it to be a really kind of like hot, an experiential part of the habitat design. This was our concept for the working spaces. And the idea here was that we would liberate the entire central space. And that allows for, increased communication, increased light distribution, airflow, and can become almost like a multi-purpose space. This is just one idea of how you can use a space, but you can imagine enabling this space to become something like, like a much bigger communal space, or it can also be divided up for different compartments or offices. But the idea is essentially that we come up with a framework that would allow you to reuse this space in various configurations. And the other thing is that the floor systems, the way that they're distributed, allows for easier access to different mechanical systems and also the supply and resupply of oxygen throughout the habitat. This is an image of how the crew quarters we imagined it could look. One idea of many, but you can see here that we're also trying to use integration, trying to integrate different interfaces, personal storage compartments, different kinds of lighting mechanisms, and of course, you want to have enough central spaces for working together. In terms of radiation, there's two types of radiation that you want to protect from, so SPEs and GCRs. And one of the things that we tried to look at, of course, the thickness of the material on the outside of the habitat, but also potential for increased radiation protection in the form of either water by lining the inside of the habitat with water, or using ISRU to shield the habitat from the outside. And what you see on the bottom is the thickness of the material. And this graph just shows you how, as you increase the thickness, the radiation, exposure goes down. But it also gets to the point where at some point you can't send all this material, so you have to come up with ingenious ways of either hybridizing your internal structures with, like I said, water or high hydrogen content materials, or coming up with an ISRU capability that would allow you to shield it from the outside. But for a preliminary architecture like this, I think we were really depending on having everything integrated, so achieving the minimal shielding requirements that the habitat needed, but also potentially thinking about how you would connect additional shielding to the exterior of the habitat. And then here you can see a cut through one of the window frames in the shell interface. And the idea here is to, of course, provide structure, thermal, radiation protection, and what these translate into is safety, performance, and comfort. And I think just looking at the number of layers, in this case, we have about 10 different sections for the layers. You can see that it's quite intricate, and we were able to achieve that conceptually, within a thickness of about 300 millimeters. Although that can change depending on how these different technologies evolve. But the idea was essentially that we would have the central frame tie into the shell either through a series of loops, or maybe it's fabricated as part of the external shell, and then that the loads would all be transferred to the frame. And the geometry allows you to transfer those loads as seamlessly as possible. In terms of life support, by working with our team, our partners at ESA, we were able to understand a lot of the different nuances in terms of life support. But essentially, the crew interfaces with the different resources. And so what you see in the middle, oxygen, water, radiation protection, crew labor, crew waste, ISRU, EVA, habitation, power control systems, all of these translate into systems that will eventually interface with the resources that the crew need to work and survive. Power is also a key driving factor, as I said before. In this study, we did look at power requirements for transfer. In order to keep the hardware working, you want to achieve something like 10 degrees Celsius for the transfer. But then once you're on the surface in full operation, 22 degrees Celsius is a pretty good number. But the transfer power requirement was about 11 kilowatts. And that means that you have to have either some, solar energy generation capability on the outside, or you want to have batteries on the inside as well. At the same time, we looked at the different kinds of illuminations that you would have given a site on the South Pole. And there's been studies that show that you can get up to 92% of continuous illumination if you go at a height of about 2 meters off the ground. But to be conservative, we targeted 80% if we are going to be using, a combination of a power station, a nuclear power station, and solar energy collectors. But like I said before, in this scenario, there's a huge mass penalty with using solar panels. So we wanted to make sure that the fission reactor system was kind of like the key driver here, which weighed about 5.6 metric tons. This was really unique to this concept because the structures, as you can see, becomes kind of like the character of the habitat architecture, but also one of the biggest mass pieces of infrastructure. And so this is a breakdown of the overall structural frame. But what we did was we tried to look at the different floor configurations. So there's possible configurations that could help improve the optimization of the amount of material that you need in the floor and also the frame. And in the images on the bottom left, you see that we use a concentric frame, one where the perimeter frame actually follows the form. But then we also have a configuration where they link directly. So you have a triangular frame, which could become kind of like a secondary primary structure for the floor. But then you would have these kind of like outriggers that would project out to support the panels that the crew would be walking on, and also that you would attach all the mechanical systems and ceiling to. Give me a second here. Right, so this is an animation just giving you a 360 of the breakdown for the habitat. I mean, it's very clear here. It's a 4-story configuration. And, you know, depending on the kind of mission scenario that you're looking at, this could be scaled down to either 3 or 2 stories. But I think one of the key drivers for this was to try and look at, you know, what would be the most optimal solution for a long duration mission. And then, of course, developing that methodology, developing that framework that could eventually evolve over time and can become scaled to meet a specific, you know, mass capability for getting it into orbit and down to the surface of the moon. And so, like I said before, you know, this is one of the ideas for us that could help eventually, I think, inspire new thinking about habitat architecture, which could be in the future developed into something like, you know, like a base on the scale of a base. And so if you imagine, you know, the kind of like the first elements that need to be delivered, a habitat would be one of those. And then that could evolve over time. Either you can scale it up, or you can start to test new kinds of capabilities that would allow us to do things like ISRU or even in situ construction. And this becomes the vision, you know, it's a very ambitious idea, but it's something that needs to be conceptualized in order to get people, you know, working on these kinds of concepts. And so with that, I'll lead off to any questions.
That was such an intricate presentation, and I learned a lot. I'm curious, you know, like some of our attendees, they're interested in space architecture and probably wanted to become one or already one. And thinking about that, our space field is such a strict field, and there's seemingly there's no such a, you know, space for imagination for us as architects. So what do you think that the main constraints for designing space habitat in terms of you know, meeting these constraints of our space, as well as imagining the new way of living, right? Because we are living in a 1/6 gravity on the moon. So what are those constraints? Like, kind of summing up, because you already gave a lot of insights on the presentation.
Yeah, absolutely. So I strongly believe that, especially in practice, we have to prioritize the concerns of today, and those concerns come in the form of, you know, how we relate to the environment and how we can help improve the human condition. And it's not about excess. You know, space architecture sometimes can be a little bit excessive, and if you can start to identify what those kind of key drivers are, the metrics, whether it's, you know, thinking about comfort or energy performance or the life cycle of a building, then you can start to inform your design in a way that helps improve the quality of life for everyone. And space architecture helps kind of create those mechanisms, you know, as a as an inspiration, you can start to think about the different metrics like volume or area and energy, all tied together to help us develop a better world. And that is, I think, a big part of, I think, architectural thinking that needs to evolve more and more.
I could see that, wherever we create in space, it's all about accelerating a technology in space, and then we widely use this technology on Earth. So I was thinking about if we are designing such concepts like the moon village and eventually it's going to be implemented, how the space architecture that is implemented on other planets or in just in outer space, what are lessons could be applied to our living. Like, for example, I really like what you're saying about creating sort of synergy between systems, and then we're talking about lightings and windows, and then how would you combine those things into one, thinking about multi-purpose use. So what you think that would be useful to use in our daily life on Earth?
Yeah, definitely. So like if you like a little bit more abstractly, but if you look at the different philosophies of how we do space exploration, one is we're all working together, and one is I'm going to get there before you. And so I think the philosophy of working together is obviously what's going to happen in the next generation. Now we have industry working with us, we have different partnerships taking place, and that's the only way that we're going to achieve things as ambitious as going to the moon, right? But then I think from a more kind of like down to earth side, we have to open up conversations to working with other partners, whether it's in academia or science or industry. And I think just having that flexibility in the process of design, instead of speaking to ourselves, because especially in the field of architecture, we tend to speak to ourselves, and we look at the things that we do from from the lens of an architect, and then that sometimes limits the conversation and how far you can advance the integration level. Yeah,
Absolutely.
or the level of integration.
Yeah, I also, in my opinion, developing space architecture is not only about space. It's even not. It's almost nothing to do with space. I think it's just the way how you think about the problem. It's really a mindset. It's about creating, making sure that you fit everything in extremely small space, and it doesn't matter whether it's in space. Well, when we're designing for space, there are much more requirements in terms of materials, so there should not be off gassing. And then, but at the same time, we are facing this crisis, really, step by step, of climate change, and we are already talking about floating cities, and urban overpopulation. People are still moving. There are more and more people moving to cities, and we are pretty much our places becoming smaller and smaller. And there's a movie like it's called Downside. It's like about scaling down humanity so we can fit. It's really such a fun concept. But yeah, I think that working together, as I said, working with non-space and space entities, and it's like that's really fascinating to me that SOM is American architecture office, and you worked with European Space Agency, and this is just feels like there's no boundaries between creating a better future for us, in order to become multiplanetary species. That's
Absolutely.
yeah.
And then you have to give credit to the leadership, because without their support, this wouldn't happen.
Absolutely.
And it's a leadership from every side, from ESA, from SOM. But it happens. I think it also is like a bottom up process. More creative, maybe like creative individuals who haven't had enough experience in the realities of the industries. They come up with these ideas, and then all of a sudden, it helps generate something new. And then as you confront the realities, you kind of start to like lose sight of these larger visions.
Yeah.
This is something that like look at creatives like Elon Musk. He's doing some amazing stuff, and he still has
You
it
called
like
him creative. That's I love it
curiosity.
a lot. Yeah,
Yeah.
you call him creatives.
So there's a lot. Yeah, there's a lot to do. There's a lot to contribute, and I think if we all work together and find a way to help inform whatever we do by working
Yeah.
with others, it helps, definitely helps enrich the overall experience of coming up with new ideas.
That's I
Yeah.
absolutely agree with you. And you don't need to be a rocket science to obviously to join, space industry. There's so many opportunities opening up every year. And I got this question about that. Many people think that 1/6 gravity on the moon is such a constraint. But same time, I think that this is really about how would you creatively, solve this problem, or if it's, or for you, is it not a problem? So, what do you think? Whether 1/6 gravity is an opportunity to explore, or it is a constraint for us as an architects?
Yeah, definitely, it's an opportunity. So in the case of this habitat that we just talked about,
Mm-hmm.
the ceiling heights are a little bit more generous in a typical like living unit, and so the idea was to try and take advantage of the partial gravity so that you could make use of that higher elevation. And also, you can see in the images that there's a lot of equipment to interface with, but it's about the surfacing, the design, the integration, and so you make use of as much surface area within that space as possible. And if you can reach higher altitudes with a little bit of assistance from some bars or restraints, then you can have a completely different experience of your living or working space.
Yeah.
Yeah.
And I think some of our attendees wondering, how did you end up being involved in space industry? How did you start? Because all of our, space architects, there's not so many in the world, and each of our ways are so much unique, and that's really be interested to hear your story, like pretty much a short story kind of outline how you started and how you see yourself in the future and how you see the field evolving.
Yeah. Yeah, I've always been fascinated by kind of like the science of architecture, and like as a kind of, I would say, a more general term, because architecture and science don't necessarily come together. Like architecture is a
Yeah.
liberal art; it's very much an artistic, I think, part of history. But also, in today's world, architecture is a technology. And when I first studied architecture, I looked at it, philosophically, artistically, culturally, and then I started to develop kind of I think, an expertise in digital tools, and that led me to looking at how construction to achieve artistic expressions in architecture was being used, so in a different way. And you can see that it's all about communicating information, and if you can communicate information effectively with the people that are trying to build your vision, then all of us, you can make it much more achievable. And technology allows us to do that. It allows us to integrate design. It allows us to communicate information. It allows us to participate in different disciplines. And that's also what got me involved in space a little bit, because I had an interest in technology, and that technology migrates. It's being used in space. It's being used in the building industry. It's being used somewhere else, and you can bring these different ideas together through technology. And that's why at the beginning I said technology as inspiration, which is kind of what we're living in today. Technology
So
is
I can see that you like to solve complex problems, because designing for space is one of the complex architecture, uh, you know, ways. And there is so many questions that I received, and let me ask you first question. So the what strategies are there for dealing with the effects of microgravity in space over the long term?
Yeah, so that's not my line of expertise, but I can only imagine that medical tools will be used, that you'll have different kinds of, I guess, operational strategies, how people, live on a daily basis. They would have to do enough exercise to, just to basically like hold back the effects of partial gravity because you have reduced, bone mass, your muscles deteriorate. So you really have to work hard at conditioning yourself. And,
Absolutely.
not all of us are athletes, but an athlete would be more, I think, equipped to do these kinds of things.
Yeah, absolutely. And I think I would add that, yeah, this is not the area of expertise for architects, but it's really important to realize that architects should work together with human factors specialist, with the psychologist. I'm talking about mental health, right? Because mental health is also going to be affected.
Oh,
And
yeah.
yeah, just space medicine, because space medicine is developing and evolving so fast. And then there's grants that provided by NASA, like Trish grant, that is focusing on such problems and how actually design can well, we some of the space architects, they're industrial designers, and we work on towards developing a new tool for exercising, for example. And this is one of the criteria, um, you know making sure that the strategies for dealing with the effect of microgravity space are considered, because this is one of the biggest issues that needs to be addressed.
Yeah, I think to that point, like psychologically, I
Yeah.
think like, for example, if you think about, we use imagery a lot to communicate our ideas. And so visuals become kind of like this feedback loop to help us achieve a desired feeling out of architecture. And it's all about, how do you extrapolate the information in what your design intention is to how the human responds to it. And so you can imagine, coming up with a concept for an interior space and then replicating that concept either digitally or even physically, and then having some kind of like sensory equipment that would allow you to detect how people behave, biologically in that space. And so there's a lot of tools at hand. I think we just have to learn how to use them and be willing to use them. But it's all about feedback loops. You just have to find a way to take that information and help it inform your process. And I think if we can do what we do with like physical models and renders, from an experiential perspective, then you can definitely inform it in a more scientific way.
Yep. So the structure modular? Could you separate different floors and transport them individually, which can be assembled on the surface? So this is a question. And then this approach could reduce the mass and the budget requirements.
Yeah, the assembly, if you were to break it up and then assemble it, I think it would complicate the mission. You would have to have equipment, you would have to have crew operate to build it. I think it would just be a lot more complex, especially since it's a vertical configuration. And so that makes it even more difficult because you need to have other pieces of equipment to stack the different pieces of structure if you were to do that. But in this case, we designed it to be completely integrated. And so the idea was that, this gets built on Earth, it gets assembled, outfitted, and then you ship it in its compact configuration. And once you get it there, if you can get it there, then you deploy it and you operate it.
Do you think that these habitats could be is going to be assembled by robots or by humans? This is my question.
Yeah, I think it would be a combination of both. You would have to have some kind of teleoperation, and you would have to, maybe not humans in the physical sense, like you wouldn't have them lifting things on the surface, but maybe you would have some oversight and surveillance to be able to monitor what's happening in the sequencing.
Mm-hmm. And the other question is how you start the process. Like during the early design phase, did you outline any minimal architecture requirements, such as square feet per inhabitant, private public space ratio, minimum heights, etc.?
Not to that level of detail. I think the beginning, like I said at the beginning of the presentation, was that we had some mission requirements like number of crew, duration of the mission, and we had a general sense of, what kind of like the environmental drivers were. And from there, we just had a series of conversations to help evolve the design and help improve it. And that actually led to a study that we did a little bit later after we signed another agreement with ESA to do a CDF. And that CDF really helped advance the technicalities of that architecture. and that included things like life support, energy, GNC or guidance control, sorry, GCN, guidance control and navigation, like just a bunch of different factors that we don't know anything about, and then that would help us become better integrators of the concept.
Mm-hmm.
Yeah.
But what CDF stands for?
It's a concurrent design facility study. So it's a technology that ESA has where you essentially bring a lot of experts into a room and you have them working together to help come up with all of the different necessities for developing an architecture, whether it's like a habitat or a satellite or any kind of mission. Yeah, it's almost like a rapid mission design team.
Sounds great. And then interoperability. Interoperability is one of the Artemis Accords principles. How can different settlements or architecture elements become integrated together? For instance, standard airlocks, etc.
Yeah. So I think they just answered the question, but it was like you have to standardize. You have to standardize components. You have to standardize, how things come together. You have to standardize the kind of power that you use. You have to standardize different interfaces. So this is something that you can only do if people are working together, and especially if the international community is involved.
Absolutely. I think that one of the most important thing is transportation vehicle. It's what actually differentiates space architecture from architecture, because in architecture you almost are limited in your possibilities. Like you don't think about what kind of transportation you're going to use, and but in space architecture, the initial the first step that you probably do is making sure that you researched on vehicles that are available, that you're going to carry your habitat, and then calculating all the mass and volume, as you already mentioned in the presentation.
Mm-hmm.
Yeah, absolutely.
I think the biggest challenge there is that we have for example, the SLS, which is not reusable. So if you wanted to, but at the same time, you're also limited in mass capability. But then you have also a new technology like the Starship, and then how they're developing that lunar lander as part of the Artemis program. So if you can imagine, if they achieve that, if they can achieve a lunar lander that can take something like 100 metric tons to the surface, then you enable a completely new paradigm of architecture. And and then habitats are no longer like these kind of like stacks that are integrated into landers and are not reusable, but then they can become reusable completely.
Yeah, and talking about Starship, well, its initial purpose to send people to Mars, and this concept of pretty much a space airline's gonna send up to 100 people to Mars, and it really also implies that this vehicle going to be used in weightlessness as well as on the surface. How do you think it's feasible concept, and if you think it's feasible, when it's going to be feasible?
I have to say, I think 100 people is a little bit ambitious. I don't know how the math works, but I mean, just like from doing this study and looking at how much it takes to support a crew of 4, I don't think you can send a crew of 100 people in a Starship the way that it's currently designed. But I mean, it's a great idea to be able to send that many people. You would just have to look at the realities of how it can be developed. Yeah.
Yeah. And this is the question that I'm gonna ask. It's really, I'm also curious about this question a lot. So, could you outline the time frame for different types of habitats in terms of feasibility? For instance, pressurized modules, inflatables, RSIU, dome structures, cylindrical structures, etc. And also, is there a way of creating space architecture that has any like sort of whimsical shape, or just pretty much when we build iconic architecture on Earth, we pretty much not restricted with shape, right? But how do you see these non-restrictions on shapes implemented in space sometime soon or ever? Yeah.
No, definitely. It's a combination of both. Of course, you're going to have designers working on this stuff. So designers always have, not only one given design for, like if you wanted to build a structural shell, you could do so many things, but then you would have the constraints of how much energy it would take, how much time it would take, the cost associated with constructing something on site. So yeah, there's like, I'm answering the question about ISRU construction, but I think there's a lot of potential in doing that kind of work. It's just that the machinery that we use to construct on Earth is not the same machinery that you're going to use in space. And it has to be invented. It has to be completely designed, like re-engineered. And that's something for somebody else to solve. But once that machinery is there, you'll definitely have designers wanting to design all kinds of things that, can either be like improve, higher efficiency or lower efficiency. And there might even be different philosophies about how you design in situ structures. And of course, it's like on Earth, you'll have different attitudes about what architecture is and how that relates to the way that you think about human activity.
Absolutely.
Yeah.
And there's other question regarding tools. So, space architecture tools are essential in order to make sure everything is going to work and everything, as feasible as possible. And a lot of analysis are necessary to make this design a reality. And what kind of tools you use at SOM, if you can disclose that.
I think I can maybe talk abstractly about the tools because we use a lot of parametric tools, computational tools. There's a difference between parametric and computational tools. Parametric tools are something that you can develop kind of on a custom basis, and you can develop them to take different inputs for parameters, and then those tools can help you design something like a structure or an enclosure or different kind of interior space. And then computational tools allow us to take different kinds of physics, like different formulas that can then also not just help you design or generate designs, but also inform or analyze the way that your ideas are behaving. Like we do, for example, we do daylighting analysis, we do irradiance analysis, we do finite element analysis, we use computational fluid dynamics, and then we even use evolutionary evolvers, evolutionary modelers. So there's all kinds of different tools that you can use. And then of course you have Excel, which is like the best tool for everyone, because Excel, you can email it to anybody really quickly and they're like, oh yeah, there's a parametric model, and you can share information or spreadsheets. But yeah, there's all kinds of great tools out there. Visualization tools, analysis tools, design tools. Everything's about communication,
Cool. Okay, I think we'll go with the last question. And this is also so a question from Bonnie. NASA doesn't appear to hire architects since I have been looking for years. How did you get your foot into the door, and is that still a good way to get into space architecture?
NASA? I don't work for NASA though.
Yeah.
No,
well, I have some answer to this question,
yeah.
but I want to hear your question, your answer first. In terms of how would you get your foot into the door in order to work on these projects?
Yeah, that's a tough question. I think it's timing, and also just being very ambitious and get passionate about the work. I think if you wanted to develop your own, ideas for how you integrate habitat architecture into whatever you do, it's all possible. But yeah, it's not easy to start a company in space, that's for sure. So if you wanted to work for a company like Blue Origin or SpaceX or some other space company, then you could easily apply. And things are evolving. So, space architecture is becoming more of a serious kind of question, like how are we going to address these problems? And it might not be in the form of habitat architecture, but you can imagine, there's some need to think about like interiors or experiential design, or even thinking about things like, preparing the site for landers, because as landers get bigger, you need to come up with strategies for, hardening the ground or there's all kinds of ideas out there. You can get involved. I'm pretty sure it's just a matter of like keep looking and talk to the right people.
Yeah. So I absolutely agree with you. In my experience, it was usually work for free, get the stuff done, work for free, because all the projects that I worked in, most of the space architecture projects, they're not funded because there's no stakeholders. They are appearing to exist, but there's no stakeholders yet exist. And I'm not talking about NASA, Johnson Space Center, for example. There are space architecture. I studied space architecture program at University of Houston, and all of our alumni who are Americans, they are able to work at Johnson Space Center as I would say that mostly as systems engineer rather than space architect. So it's pretty much the same. So you there's less consideration in terms of aesthetics and more in terms of how you actually bring habitats to life and how it's actually going to work. And so far, it's mostly engineering field. Um, in terms of where you can get paid, right? Where you can actually establish a career. But I also was struggling with that a lot because I wanted to see the change. I wanted to kind of, as Daniel said, it's all about timing. It's all about understanding where NASA is hitting and all our major space agencies and what are our plans towards establishing lunar uh, bases and living on Mars and living in space station on a space station. It's really all about persistence, all about really wanting to work in this field, and eventually you'll find out how to make it as a career. There's no such a one way I can suggest to do. This is just be passionate, ask questions, ask space architects like us what we what we're doing, what how we've done it. And there's no, as I said, no as such a single way. And space architects are different in terms of what projects they're working on. Some of these extremely, technical projects. Some of them are just pretty purely conceptual. So it's
Yeah,
really about your choice whether you want to work on these appealing visions of colonizing space and then pretty much working as an artist. So there's at NASA GPL there is a studio called Studio GPL where artists and designers working on these visions, and this actually poster. This is popular posters from GPL, and probably everybody has it in their homes almost. And uh, and
if I can
yeah,
just
mhm,
if I can just add to that, I think like
absolutely.
what you, yeah, I think what you said. So of course it's an art that you develop over time, but you want to make sure that that art is also benefiting something that you do in practice. So like in if you're in the science world or in the art world or the architecture world, find a way to get these ideas to benefit an application that exists today. And you can see that that's what these huge entrepreneurs are doing. They have companies that help support these large ambitions, and those companies are benefiting from practicalities, and it's all kind of like leading up to this much longer vision. So it's really like long term. You have to rethink. You have to think long term, and that is really difficult to do, especially on a day-to-day basis where there's so many people interested in what can be done now. So, yeah.
Yeah, talking about my personal experience finding Stellar Mentis, and it's this space architecture company that's actually not only focusing on space application, but just real life this principle of designing for small spaces, and it doesn't matter which space you consider, and addressing these challenges that we are facing right now in terms of pandemic, in terms of living small spaces as you know uh, in overpopulated places and urbanized places, and this is where I think our knowledge of space architecture could be applied right now. and this is the market that we are working towards on in terms of stellar amenities projects. We are working on deployable lightweight solutions for office spaces, for tiny houses, for underground, underwater facilities in the desert. So there's so many opportunities that you need to really seek for, and you will have success if you're not giving up on this idea.
Absolutely.
Buy my courses. Just kidding. I don't have any courses. Anyway, it's more than 12. It's 12:06. Well, it's in my time. We are over time. We're kind of running out of time.
Mhm.
It was such a wonderful conversation. I extremely enjoyed that, and I believe that attendees also enjoyed conversation as well. We pretty much answered most of the questions, and the I really adore the intricate presentation that you gave to us, and I really like that you worked with the team that considered all of the aspects of space travel as well as architecture. And well-being in space is something that is probably one of the biggest uh, you know things that needs to be resolved when we're thinking about long duration missions and sustainable development of space exploration. And this is actually the reason why I just decided to host space architecture talks. Is just to realize and show how design and architecture are the tools towards successful becoming a multiplanetary species, towards successful living in isolation, because we are all about space exploration is all about living in isolation, living with the same people all over again, and then how you make sure that these spaces that you design are changeable, are reflecting the needs of our users. And this is extremely fascinating field, and there's more and more people coming and working on this, and I'm just really happy to see that we are able to come together and collaborate on projects. Yeah, so my last call is like dream big, and yeah,
Yeah,
continue working on your projects no matter what. Believe in your vision and be persistent with your ideas. I think I'm giving like a business
there's
uh
more to come soon.
cacao exactly couch thing.
All right.
um all
Thank you very
right.
much, Nastasia. That was nice.
Absolutely. Absolutely. We need to
Yeah.
repeat someday. And just really hope to see you soon, and to return back to these physical interactions. And uh, yeah, thank you
We'll
so
be
much.
releasing we'll be releasing some more information on
Mm,
what we've been studying. So I will share it with you, and you can also share it with anybody that listened today. So
absolutely.
stay tuned for some more detailed information on space architecture.
Yeah. So you
Yeah.
can follow us on social media. So it's Stellar Amenities tag, and then I will post there some more updates from Daniel once they come. Hmm.
All right.
All
Well, thank you.
right.
Have a great day.
Thank you. Have a great day too. And then for all of the attendees who are staying with us, there's gonna be a 15 minutes networking session. And if you want to meet and greet some like-minded people, please stay with us and enjoy. Thank you.
Yeah. Thank you very much.
Bye
Bye.
bye.